Bigger turbochargers are often assumed to make cars faster. More airflow should mean more power, and more power should mean more speed. But in real-world engineering, that relationship is far less direct. A turbocharger's size determines how much air it can move efficiently, but it also determines how quickly it responds. Larger turbos have heavier rotating assemblies, which means they require more exhaust energy to accelerate. That additional inertia slows response, especially at lower engine speeds. This creates the first major trade-off. A larger turbo may produce more peak power at high RPM, but it often delivers less usable power during normal driving or acceleration. If the engine spends most of its time below the turbo's efficient operating range, the extra size becomes a disadvantage. Acceleration depends on how quickly torque is delivered, not just how much power exists at the top of the rev range. Two engines can produce the same peak horsepower, yet accelerate very differently depending on how early and how consistently that power is available. This is why dyno charts can be misleading. Dynos measure peak output under controlled conditions, but they don't show how quickly the engine reaches that output. A car with a smaller, responsive turbo may feel significantly faster in real driving than a car with a larger turbo that only performs well near redline. Engine airflow demand also matters. An engine can only use the air it is capable of processing. If a turbocharger is oversized relative to engine displacement, valve flow, or RPM range, much of its potential capacity is never used. In those cases, the turbo is operating inefficiently for most of the engine's operating range. Gear ratios further shape this behavior. Street-driven vehicles rely heavily on mid-range torque, where engines spend the majority of their time. A turbo that delivers boost early and predictably often results in stronger real-world acceleration than a larger turbo that requires aggressive driving to stay within its power band. Thermal efficiency is another important constraint. Larger turbos often generate more heat during partial load operation. Without adequate intercooling, airflow management, and heat rejection, this heat reduces charge density and limits performance. In some cases, increasing turbo size without upgrading supporting systems actually reduces usable power. Reliability also plays a role. Larger turbochargers place higher mechanical and thermal stress on engines, transmissions, and drivetrains. Engineers must balance performance gains against durability, cooling capacity, and long-term reliability. A system that produces more peak power but fails earlier is not faster in any meaningful sense. This is why turbo selection is never based on airflow numbers alone. Engineers evaluate engine characteristics, intended use, response targets, thermal limits, and drivetrain constraints. The goal is not the biggest turbo possible, but the turbo that delivers power where it can actually be used. In controlled environments like drag racing, large turbos can be effective because the engine operates near peak output for most of the run. But for street cars, track driving, and daily use, oversized turbos often make vehicles slower, not faster. Bigger turbos don't automatically make cars quicker. They shift where power occurs, how it feels, and how usable it is. Speed is not determined by size alone, but by how well the entire system works together.